இது உங்க ஆபீஸ் சைடு தானே? ஆயா நம்ம ஃப்ரெண்ட்ல
Good afternoon, everyone. As this is the last session of our 5 days FDP, let's introduce for today's session. She is, and let us tell something about her. She has done her PhD in chemistry. She completed research project funded by SERB, DST, Government of India regarding cost-effective production of titanium metal powder through molten salt electrolysis. She has 3 patents, around 20 number of journals and conference publications. She also has guided so many PhD students. Her research area are metals, alloys, materials preparation through aqueous and molten salt electrolysis, electrochemical treatment of industrial waste, e-waste to produce various valuable materials, renewable energy like biodiesel production through utilizing electrochemically prepared catalyst production from cellulose biomass. Now I request Dr. Mohanty to keep her video on and can share her screen to the audience.
Yes, madam. I am opening my PowerPoint presentation. It will take some time. Okay.
Sure. And before that, I am telling to our participant that after this presentation, we will give you the quiz link through the chat club. To you. Yes, ma'am. Sure.
Thank you, madam, for your brief introduction regarding my research work and myself also. Welcome to all of the participants who are present in this FDP. Today, I'm going to deliver one talk regarding electrochemical approach to produce iron-based alloys from industrial byproducts. So, I think most of the topics, they are not related to any kind of electrochemical discussion has happened. I think so. But today I am going to discuss one very important aspect of electrochemical treatment of different kinds of industrial byproducts. Here, I will not use the term waste, rather I will use the term byproducts, and how the industrial byproducts, they are utilized to prepare various valuable materials through electrochemical route. That part I am going to discuss. Now, if you see terms involved in the topic or the title, there are three important terms are there. One is electrochemical approach, another one is iron-based alloys, another one is industry. So, first thing is how electrochemical treatment can produce one important structural material like iron-based alloys. As you know, iron is very important structural material. And if it contains some alloying elements like titanium, nickel, chromium, then its properties are mostly enhanced. So iron-based alloys from the industrial byproducts. And if I consider today, I'm going to discuss the two types of industrial byproducts. One is titania-rich slag, which is produced by smelting of the ilmenite. And after that, I will discuss how electrochemical treatment can produce one iron-based alloys from the red mud, which is very important byproduct, or you can say also waste also, because it contains some, it is highly alkaline. So how this material can be produced from the red mud, that part I am going to discuss. So section, first let me provide you what is an electrochemical processing of metals and alloys. That is, when you are preparing the metals or alloys from their ores directly through electrochemical route by dissolving the ore in a particular then that concept is known as electrowinning. Now, if our knowledge says that there are many industrially many metals are produced by electrowinning. If you say copper, you can say also zinc, also lead, then gold, produced by the electrochemical process. And if you are preparing the metals or alloys directly from the ores, where the ore is dissolved in a particular electrolyte, then that concept is itself known as electrowinning. Now, what happens in the electrowinning and how it carries, how it is exactly carried out? Basically, the electrowinning is carried out in an electrochemical cell, which consists of two electrodes. One is cathode and anode, where the cathode reduction happens, anode oxidation happens, and the electrolyte is one liquid material which is highly conducting. So the electrolyte can be the direct solution of the ore, like copper sulfate. You can take copper sulfate, you can deposit copper from the copper sulfate, or you can deposit zinc from the zinc sulfate. It can be directly the zinc sulfate or copper sulfate, or it can be one conducting medium in which the ore is dissolved, like aluminum electrolysis. In aluminum electrolysis, what happens? The ore is alumina, Al2O3. And where you are dissolving alumina in one electrolyte like cryolite, Na3AlFCs. So when the ore is dissolved, then it is in the solution form. So when you are passing the electricity, your metal ion like aluminium 3+, they migrate towards cathode, and your anion part goes to the anode. At the cathode, the aluminium is reduced to aluminium metal. So here you are seeing that the ore is dissolved, and in another case, you are directly taking a salt or a compound of the metal ion, so that you are directly depositing the metals. So whatever may be the process, all the processes are called electrowinning. So let us first see which kind of metal we can produce by the electrowinning methods. You can produce lead, copper, gold, silver, zinc, aluminium, chromium, manganese, and most of the alkali metals also like sodium, You can produce sodium, alkaline earth metal like magnesium, calcium. They can also be prepared from the electrolysis method or electrowinning. Now, we can see very simple diagram through the electrolysis. This is a very simple concept, like how you are depositing copper from the copper sulfate, and here how zinc is produced from the zinc sulfate solution. And you have seen there are two electrodes are there at cathode. Zinc is deposited as zinc metal, and at the anode you are getting some oxygen gas due to the anode reaction or oxidation reactions. Similar thing also in case of copper also. Now look at to these two reactions. You can see that in both the cases, the electrolyte is aqueous, or electrolyte is dissolved in the water, dissolved in water. So this kind of metals, they can be produced through the solution or from the solution that are dissolved in the water. And such kind of electrolysis is known as aqueous electrowinning. Basically, we'll come across different kinds of electrolysis or electrowinning. First, I am discussing the aqueous electrowinning, where the metal like copper, you can deposit zinc, you can deposit through aqueous electrowinning. Is basically the medium, and you are dissolving the substance or the material from which you are depositing the metal ions in the water solution. So in that part, these two kind of electrolysis is known as aqueous electrowinning. Whereas another kind of now you are seeing this, you can see also here how industrially the copper is produced through the electrolysis. These are the copper cathodes. So in industrial level, you cannot put one electrode, you have to put many number of electrodes. So, and they are connected in series and be like this, so that you are depositing copper. Here you can see the zinc is placed by the electrolysis and the electrodes are there. The metal is deposited. After deposition, the metal is scratched out from the electrode, and there then other processing will take place. And then the next thing is, we are coming up that apart from the aqueous electrowinning, there is another kind of electrowinning is there, that is called your that is fused salt electrowinning or molten salt electrowinning. Now, what is the difference and why we use fused salt electrowinning and not in the aqueous electrowinning every cases? Basically, if you see, there are metals, some metals are there, they have high reactivity towards oxygen, water, and these metals are alkali and alkaline earth metals. So if you are considering the deposition of alkali metals like sodium, you cannot prepare in the sodium metal in the NaCl solution by electrolyzing NaCl, because water is there. How can you, because sodium has high reactivity, so it cannot deposit in the water solution. Besides, there are many other factors are there why we cannot deposit the sodium metal. So what you will do, you have to carry out your electrowinning process in the fused salt. So one term, new kind of electrowinning comes, that is called fused salt electrolysis, where the electrolyte is in the molten state and it is not dissolved in the water. So what will happen? In the molten state, the ions are present. Definitely the system is in the ionic state, but the water is absent, so that whatever the sodium or magnesium or calcium they are deposited at the cathode, they won't react with any kind of oxygen or water, and they are directly coming, we can extract it directly and we can keep it in an air-free region. So that is the basic principle. Electrolysis, you have taken the molten electrolyte, and you see you are taking cathode and anode. In this case, the iron is the cathode, carbon is the anode. Carbon basically it can be graphite. So what will happen? The sodium from the NaCl will be reduced to produce sodium metal, and carbon at the carbon anode you are producing chlorine gas. So, and extracting the sodium metal here. Similarly, you can think in case the magnesium is produced from the electrolyte MgCl2, NaCl, and CaCl2. You have 3 electrolyte, and that is also some reason is there why you have taken the 3 electrolyte. But we are extracting magnesium. So magnesium chloride is mixed with sodium chloride, calcium chloride, and during electrolysis you are producing magnesium, and due to the lesser density it is at the above the electrolyte, and you can extract this metal from the system. Now you can see here there is also no water. It is water-free region or medium where we are only taking the fused or molten salt. So industrially also using two types of electrowinning. One is aqueous and the fused cell electrolysis. Basically, fused cell electrolysis is used to extract the metals which are highly reactive. So reactive metals are extracted from fused cell electrolysis, whereas noble metals like copper, zinc, gold, they can be extracted from aqueous electrowinning. Now, we'll come across the various kinds of electrowinning. So basically, if you can classify the electrowinning process from extraction or extraction, it is of two types, aqueous as well as fused. So as I have already discussed, noble metals can be extracted through aqueous electrowinning, whereas some reactive metals like aluminium, magnesium, titanium, sodium, they can be extracted from their fused salt electrolysis or electrowinning. Now the question comes, why should we treat the materials by electrochemical method? Why not by any other method? Because many methods are there available commercially. You can extract the metals, like you can go for carbothermic reduction, you can go for thermic reduction. So these methods are there. But why we need some electrochemical treatment is that there should be some advantages for that. Only we are preferring electrochemical method to produce certain metals by electrowinning method. So first thing is, your basic advantage of this electrochemical process is it can extract the metals or alloys or any materials with high purity. The purity of the product is maximum. In a why it is maximum? Suppose I am taking a mixture of copper sulfate and zinc sulfate solution, and normally if you want to get the copper and zinc from the solution by chemical method, it will be contaminated definitely. And in chemical method, what you are doing, you are adding some reductant, so that another reductant is added and a chemical is added to the system that may contaminate your copper and zinc metal. Besides, there is simultaneous precipitation of this copper and zinc from the solution may take place. So you cannot separately extract these metals. But in electrolysis, what will happen? Though there are many metal ions are there, but if you control the cell potential, or if you can control the reduction potential of the metal ions, then you can selectively extract the metals. So what will happen? One metal is in the solution, another metal is in depositing at the cathode. So you are selectively extracting the metals. For that only, the purity level is very, very high. Besides, you are not using any kind of external reagent or reductant to reduce the metal ions. Now, what is the reductant? Reductant is the green redox reagent, electron. So only electron is passing through the system and it reduces, and two processes are taking place. If reduction happens, definitely oxidation happens at other side. So by this process, what you are doing, you are not adding any external chemical reagent. Besides, you are producing the metals in a very high purity. And the third thing is that there is no byproduct at all. Where the byproduct will come? Because you are only depositing the metal through the electron. So there is no byproduct for the processing, or you have to throw it to the environment. This is the basic reason it is a very environmental friendly process. So for this reason, where the purity is a concern, and where the environmental factor is a concern, and where the byproduct processing is a very difficult task, then only people take the condition like electrowinning or electrolysis process. So that is the basic advantage for which many metals are produced by the electrowinning methods. And the very important example is aluminium. You know, aluminium actually initially it was produced by your carbothermic or metallothermic reduction, and it was very difficult. the cost of aluminum was very, very high. But when the electrolysis come, the aluminum metal cost is drastically reduced because it can produce in industrial level, it can produce in high purity, environmental factor is definitely it is reduced. So this is the basic advantage why we prefer this kind of technique for extraction of metals or alloys. Now let us see some concepts regarding the fused salt electrolysis. Why I prefer to describe fused salt electrolysis, as I discussed that although there are two types of electrowinning methods are there, but in this particular topic, I am going to discuss regarding the fused salt electrolysis and how fused salt electrolysis is applicable for producing the various iron-based alloys from the titanium slab and red mud. So this part, since I'm going to discuss, so I will definitely make some insight into the fused salt electrolysis. So there are many active reactive metals which can produce by the fused salt electrolysis. If you see the mechanism or process through which the fused salt electrolysis is happening, it is of two types. One is, if you are interested to deposit one metal, considering aluminium. In this case, what we are doing, you are choosing alumina. And alumina is a non-conductor. The first and foremost condition for electrowinning is you have to choose two electrodes which are good conductor. Cathode and anode should be good conductor. Electrolyte should be good conductor. Otherwise, you cannot carry out the electrolysis. So first thing is aluminum electrolysis. Aluminum is extracted from Al2O3, alumina, which is completely one insulator. So how can you produce aluminum from alumina? So you have to choose one's medium or one solution or electrolyte which is conductor. So that is called cryolite. Na3AlFCs, it is ionic substance. So ionic material, they are highly electrically conducting. So Na3AlFCs is the electrolyte. In the electrolyte, you are dissolving the alumina, Al2O3. So when you are passing the electricity, what will happen? I'm showing you. When you are passing the electricity, the at the cathode, reduction happens. That is, aluminum is reduced. You can see here Al2O3, Na3AlF6. They will produce this compound, and this is quite ionic. Then this ionic compound is composed to form aluminum at the cathode and carbon dioxide at the anode. And at the cathode, the electron is gained, that is called reduction. At the anode, the electron is liberated, that is called oxidation. So what is the system? The system is a container. It is usually one steel container. And this steel container is considered to be the cathode. Yes, the steel is aligned by the carbon, negative carbon cathode, and the positive carbon anode. So you can consider here, carbon is considered as both the cathode as well as anode. So what will happen? During electrolysis, aluminum is deposited and it is extracted in this path, the molten aluminum. And overall, the reaction is aluminum plus 3 carbon produces aluminum metal and carbon dioxide. So this is the basic mechanism through the aluminum. So what you are doing, you have to choose one electrolyte where you are dissolving the ore. But apart from this, there is another method of electrolysis is there. Now let us see what is that electrolysis. So this is called type 2 electrolysis or electrowinning. Don't require any electrolyte. You directly take alumina as solid. Alumina is a solid material. You directly take solid alumina powder and you make an electrode of the alumina. How you will prepare the electrode? You have to make it in a compact form by giving some compaction or making it a definite shape so that it is quite hard so that it can be used as the electrode. Electrode means electrode can be two types, cathode and anode, but you have to take the oxide or alumina as the cathode because you want to reduce the alumina. So what I'm doing, in this way, the cathode material is the compacted form of your alumina powder or solid, which is considered as the cathode material, which is reduced during electrolysis to produce aluminium. Difference. In this case, the metal is produced in the solid state because you are reducing the alumina solid directly. You are taking the powder directly. You are compacting this powder in a definite shape. It can be circular, it can be square, like you can make it any shape. Then you attach this compacted form to a current collector like a rod, conducting rod like stainless steel or any kind of metal rod that can withstand that high temperature fused cell electrolysis, and you make it as cathode. Cathode means you have to connect it through to the negative terminal of your DC power source. And when you are doing this, supplying electricity, the oxygen from this alumina goes out due to electric potential. You have to apply that potential so that it is sufficient to kick out the oxygen or oxide from the oxide cathode or alumina cathode. And during this process, the oxygen is kicked out from the cathode, and ultimately what will happen? The solid aluminium remains. Okay, and the oxygen goes out. At anode, what will happen? At anode, the carbon is usually preferred as the anode material, where the oxygen reacts to produce either carbon monoxide or carbon dioxide. So pictorially, we can also represent this kind of thing. You can take, this is suppose it is the cathode of alumina. Okay, MO2. MO2 means any kind of oxide. You can take titanium dioxide, oxide. You can take alumina Al2O3. You can take any kind of oxide you can take, and you make a preform or compacted form, and it is connected to a current collector, and it is connected to the negative terminal of the DC source. Okay, and this one is the carbon anode. In the carbon anode, what will happen? It is also connected to a current collector, and it is the molten electrolyte. The molten electrolyte consists of calcium chloride. You can see here in the Hall-Haller process, the electrolyte is cryolite, if you remember, and here the electrolyte is calcium chloride. So calcium chloride and CaO. Why CaO? Because when you are applying a potential, the oxide from the alumina or any oxide material, they were kicked out from cathode material, and where they will go, definitely there should be some material or substance should be there. They will capture oxygen. Then who will capture? CaCl2. CaCl2 is fused salt. It is in molten condition. When it is in molten condition, it contains Ca2 plus and Cl minus. So when Ca2 plus is there, it will subsequently it will be attached to the oxide to produce CaO. So in this process, you have to apply a potential that is sufficient for the decomposition of CaO. So at this potential, as soon as the CaO is formed, it is decomposed, and the oxide is it reacts with the carbon to produce CO or CO2, depending upon the reactions of the potential. This is the basic mechanism. Now you can see in one case you are preparing molten aluminium, in another case you are preparing solid aluminium. Directly you are taking the solid alumina and producing the solid aluminium. And in this case, what will happen? It is not required that time to time you have to take out the metal, because after the part, you just simply wash it and with the water, and you will get your metal. So product recovery is very easy, and the process is also very easy. It doesn't involve any kind of harmful reagent also. You are using a very environmental friendly electrolyte, that is calcium chloride, which is highly soluble in water. So that part, on this point of view, this type of fused salt electrolysis is very much attractive for producing various reactive metals directly from their solid state. Now, today a topic is based on the production or the preparation of iron-based alloys that contains titanium, that contains nickel, chromium, by fused self electrolysis of type 2. So let us see. First thing is we before going for this type of that what kind of procedure you have to follow for this analysis. Now you can see here it is a powder form. You have taken a metal oxide, any metal oxide, it is in the powder form. Now this powder form you cannot directly use the powder in the electrolysis because it is in the loose form, to be in compact form. So you have to make it in compact form. At the center I made one hole, and this material totally it is connected to one current collector, a metallic rod, or you can take any kind of metallic wire also as per your requirement. So and this is the actually the procedure you have to adopt for this kind of electrolysis. Then the next we are doing is the electrolysis, actual electrolysis. How it is happening? You have to take one graphite crucible because graphite or carbon is used here as the anode material where the oxygen reacts to produce carbon monoxide or carbon dioxide. Now in this case you have to take the graphite crucible. The graphite crucible satisfies two purposes. One is it acts as the anode material as well as it is used as the electrolysis chamber also. And in that graphite crucible, you have to place the molten, you have to place the fused calcium chloride or anhydrous calcium chloride. And this anhydrous calcium chloride, it doesn't contain any moisture. And for moisture removal also, you have to carry out some procedures like heating the calcium chloride for certain time period at a very low temperature, 100 to 200 degrees centigrade. That part is carried out because it is a fused cell electrolysis and we are producing reactive metals, so we don't prefer the presence of moisture or on any kind of contamination of water. So it can be treated. Then you have to melt the calcium chloride. Usually the melting point of calcium chloride is 773 degrees centigrade, but you cannot carry out. It is not worthwhile to use the electrolysis process at this temperature. We use the electrolysis temperature basically at 950 degrees centigrade. 900 to 950 is sufficient. Where the calcium chloride is complete, it is in the molten state, and in that condition you have to insert the material containing the oxide cathode, and the oxide cathode is connected to the current collector. It is negative it is negative means it is connected to the negative terminal of the DC source. It is connected to the positive terminal. Connected means this is graphite. Graphite is connected to the positive terminal, that is graphite is anode, and your this oxide material is cathode. Then the electrolysis is carried out, and during the electrolysis what will happen, the oxygen goes into the solution, and the calcium is there to capture the oxygen to produce calcium oxide. The potential is sufficient to decompose the calcium oxide into calcium and oxygen again, and the oxygen goes to the anode material like carbon or graphite, where it reacts with the carbon and graphite to produce CO or CO2 at a temperature of 900 to 950 degrees centigrade. So this is the mechanism of preparation of the metals from the metal oxides. And I've shown you one typical example of preparation of titanium metal from titanium dioxide directly. And from the, you can see here, this is actually a pre-treated titanium dioxide material. See, and after reduction, I am getting titanium powder like this. Solid state. So directly in the solid state, you can produce the metals without in the molten state condition, like in the Hall-Haller process. So if you see the mechanism is your metal oxide in the solid state. It is reduced to produce the metal and oxygen ion. This oxygen ion, it is converted into oxygen if you are using inert anode, or it can be converted into carbon dioxide or carbon monoxide if you are using carbon anode. So this is the basic mechanism you are using for producing the metals directly the metals. Okay, so before going for the actual topic of this presentation, that is preparation of the iron-based alloys, let us first focus what is the significance of this type 2 electrolysis in comparison to type 1 electrolysis. The first thing is we are not bothered about choosing any electrolyte which is suitable to make a ores into soluble form. We are not bothered about. We have to take any kind of electrolyte like calcium chloride. You can also take a mixture of calcium chloride, sodium chloride, where you have to dip the oxide cathode and directly reduce to metal. So calcium chloride, it is not an harmful reagent. Also sodium chloride also. They are not environmentally that much hazardous. They are also soluble in water. So their cost is also low. They are conveniently available. So for this, and another very important part is calcium has high affinity for oxygen or solubility. Calcium chloride has high solubility for oxygen, so that during the reduction, whatever the oxygen is produced, that can be dissolved in calcium chloride, and again it reacts with the carbon anode to produce CO or CO2. So that is for which we are preferring the calcium chloride as the electrolyte, and this is the most significant prospect of this electrochemical process. And what happens again? Only we are applying a constant cell voltage so that the oxygen ionization takes place to produce the metal. Only oxygen ionization. Oxygen is ionized so that metal is remained at the cathode. Coming our topic, the first one I will discuss regarding how this process is useful. Process means type 2 electrolysis or electrowinning. Fuel cell electrowinning is applicable in producing the iron FeTi alloy from titanium slag. So if we are producing the iron FeTi alloy, so let us first see that why we need the FeTi alloy, what is its importance. If you see the it is very significant material in steel industry, and because it has very high affinity for oxygen. So oxygen, and it is an additive in the steel industry. That is the most important part of FeTi. And if you see the production processes of FeTi, the various source material for the production of FeTi is ilmenite. We can also take the slag, which is produced from the ilmenite after removal of iron. So that these are the different source material, and you can use different methods like carbothermic reduction, metallothermic reduction for producing the FeTi alloy. But the electrochemical method can also be applied, because your ilmenite, whether you are taking ilmenite or you are taking the titanium slag, they are mostly the contains the metal oxides. Ilmenite is FeTiO3, so it contains the metal oxides. So as we have already discussed in this process, you directly make the metal oxide into a compacted form and reduce it to metals. So if it is possible, then it is also found that not a single metal oxide, but a mixture of metal oxide can also be possible. If FeO or Fe2O3 plus TiO2 plus ZnO, zinc oxide, zirconium oxide. So if they are mixture of metal oxide, if you are taking, then they can also be reduced to their respective metals in that particular substance. So they will give you a mixture of metals. So since ilmenite is a mixture of metal oxides, your slag is a mixture of metal oxides, they can be a source of your starting material. So you first choose the titanium slag for this process as the starting material. Now, another important point is that after removal of iron, your titanium slag, because here the iron concentration is reduced, and in this case it is quite semiconductive. The slag is semiconductive behavior. Its electronic conductivity is 10 Siemens per meter due to the presence of the titanium suboxides. So lower valence titanium suboxides provides some electrical conductivity to this material. And this provides a very it can be a good source material for electrolysis, because in electrolysis we usually prefer conducting material. So this slag is due to the presence of lower valence titanium suboxides, so it can be a good starting material production of FETI by such or type 2 electrochemical treatment. You can see here it is a ilmenite, it is powder. It can be converted after plasma smelting or any kind of carbothermic reduction or metal thermic reduction. Then they will produce iron metal. Iron metal is separated. After separation of iron metal, you are getting the titanium slag. This kind of slag material you usually produce. So how the electrolysis take place? So you collect the slag material. They are solid pieces like, so as I have already shown you. And how to electrolyze it, because in the previous case we are taking directly the powder and we are making the powder into compacted form, but it is in the lumps form, so we cannot and it is not necessary that we should make it powder and again we compact it. You can directly take it and you wrap it with the nichrome wire nichrome wire that is so that a proper electrical connection will be made. Then you dip this nichrome wire containing this slag into the electrolyte. And then what is the electrolyte? Electrolyte is calcium chloride, and you carry out the electrolysis. Okay. Another thing is that in this fused cell electrolysis involves pre-treatment of calcium chloride as well as actual deoxidation of titanium slag. So in such kind of electrolysis, first you have to carry out pre-treatment of your molten salt, because pre-treatment is highly essential to remove any moisture, if any moisture is there or any other substances is there, if they will hamper the electrolysis process, that part will be removed during the pre-electrolysis process. Otherwise it exactly purifies, or it makes the electrolyte much more that is, it purifies the electrolyte. So what will happen in this case? You can see this is a slag material, this is a nichrome wire. Taking two dots. Why I have taken? One is graphite. This is anode actually. If it is a container, rod. This is a stainless steel rod. This stainless steel rod is used for the pre-electrolysis, and it is your slag material which is connected to the wire. This system is connected to the negative terminal of the DC source, and the stainless steel rod is connected to the positive terminal of the DC source. Upon application of the potential means how much? During pre-electrolysis, we usually apply a potential of 2 volt. So what will happen in this case? If any moisture and any redox active materials are there, they are removed by this process. So first you carry out the pre-electrolysis, and when you will carry out the pre-electrolysis, first you heat the calcium chloride. I'm briefly describing this part. Okay, the pre-treatment consists of heating 100 degree first for 12 hours. Then you carry out the pre-electrolysis of molten calcium chloride to eliminate any redox active species or moisture. The slag sample then wrapped with nichrome wire is inserted into the CaCl2 mass so that the slag piece remain totally immersed in it. Then a stainless steel rod is also inserted into the CaCl2 for pre-electrolysis process or purpose. So here stainless steel rod, pre-electrolysis purpose. Pre-electrolysis is carried out at 2 volt. First you carry out like this. After pre-electrolysis, usually we carry out pre-electrolysis for 15 minutes. After pre-electrolysis, you stop the supplying the electricity. Then you remove this steel rod from the electrolyte. Again, you connect the positive terminal of the DC source to the graphite. Now you are coming to the normal electrolysis. Then when you are coming to your graphite to this, then electrolysis starts, and what will happen? And the electrolysis is conducted at a potential of 3 to 3.1 volt. it should be below the decomposition potential of electrolyte like calcium chloride. You cannot decompose the electrolyte because you don't disturb the electrolyte. Otherwise, the electrolysis will be hampered. So in this process, the electrolysis is carried out much below the potential of the decomposition potential of the CaCl2, that is 3.2 volt. So we are carrying out the electrolysis in the potential of 3 to 3.1, which is below the decomposition potential of CaCl2. So and this when the potential is like this, oxygen ionization from the slag material takes place. Oxygen comes out from the slag material and it reacts with the carbon anode to produce CO or CO2. And ultimately, what you are getting in the slag originally, it contains iron oxide, iron metal, some iron metal were also there. Then it contains the oxides of titanium. Besides, some impurities are also there. But actually, what happens after analysis of the material, we find that initially whatever the impurities like magnesium, silicon, they were present. They are not present in the final material when we prepare the FETI. So we thought that in the electrolysis process they might have been removed. So it's a good thing that we can prepare directly the FETI from this process. And yes, see here the composition analysis we have carried out, and this is a morphology study we have done for this FETI which you have prepared. And at the 2 points, you can see at the point 1 it corresponds to the titanium as well as iron, and the point 2 is it also corresponds to titanium and iron. This method provides a very simple method for preparation of ferrotitanium directly from titanium slag. And the slag also has some significant properties, like it has good electronic conductivity, so that it can be a good starting material for this electrolysis process. And another thing is this process does not need any preparation of compact electrode as in case of the other metal oxide electrolysis, because the slag is directly electrolyzed to produce the FETI alloy. And besides, after the electrolysis, we found that it helps in removal of the impurities like calcium and magnesium present in the slag material. So this is also a good thing we observed during this electrolysis. Now, we have discussed the preparation of FETI only from the slag, binary slag. Now, I'm coming into the preparation of another kind of nickel, chromium, and iron from red mode. Similar procedure is adopted, but some slight pre-treatment methods we have adopted for preparing. There is some difference there. In case of red mode, we have carried out one extra step where we have not prepared done it for the titanium slag. So we'll see. And as you know, red mode, you have already discussed many things regarding red mode. It is one important byproduct from the Bayer process, and it is highly alkaline. For that only people say it hazardous also, and also waste material. But though it is one waste material, people are saying, but it contains many valuable materials should be extracted. So a valuable materials means it contains iron oxide, it contains aluminum oxide, silicon oxide. So various metals it also contains. Now, in this process, I'm going to prepare the iron-based alloys containing Fe, Ni, Cr, Ti from the red mode. Then how we are preparing? So basically the red mode is considered as a waste material because it is highly caustic, corrosive in nature, and since it is highly alkaline, so it can directly affect our environment or our aquatic life also. So that's why the treatment of the red mode to produce various valuable material is highly essential. It is one requirement now in these days, and people are also doing many things regarding this. And at present, if you see, the red mode is used mostly for metal recovery. Metal means mostly iron. It can be used in the adjuvants. It can be used as a catalyst. It can be used as a building material also. So various ways people are using this red mode. Now, depending upon the sources of the red mode, the characteristics of the metals present in the red mode are different. In some cases, you are the metals, those who are present, they differ. So depending upon the source of bauxite material what you are using. So that's why, but mostly it contains aluminium, silicon, titanium, nickel, and chromium, and hence it can be a suitable source for production of iron or iron-based alloys. And if you see the literature still now what is available, people are using extraction of iron or iron-based alloys from the red mode through smelting at a very high temperature of 1500 to 1600 degrees centigrade in the presence of carbon as the reducing agent. And what happens? We can get the alloy material, but the byproduct slag is produced. The material which cannot be reduced, that part remains in the slag. So that slag, either you have to throw it or you have to again process it for various uses. So one extra thing you want to carry out. So in order to avoid this byproduct formation, and how we can directly convert this red mode into metallic alloys, that part we can do it by this present electrochemical technique. So since it is a low temperature operation, low temperature means if you are taking only the calcium chloride electrolyte, then you have to use the temperature from 900 to 950. But if you are using a mixture of calcium chloride and sodium chloride, eutectic mixture, then you can lower the temperature up to 650 degrees centigrade. You can produce. So at a very low temperature, rather than in comparison to the smelting process, you can carry out your electrolysis to produce such kind of alloys by this process. So what processes or what procedure exactly we are adopting, I'm saying you here. So first thing is that this process is electrochemical reduction at pre-treated red mode. We cannot directly take the red mode, rather it is a pre-treated red mode, that is red treated with sodium carbonate. So here the pre-treatment red mode is carried out in a molten salt bath to produce iron alloy containing nickel, chromium, and titanium. So if you what we observe, if you directly take the red mode for the electrolysis, it will not give you some better result. Rather, the pre-treated red mode can produce the very better result in comparison to your direct red mode material. So now I am showing you the pre-treated red mode is so how the pre-treatment is carried out. The pre-treatment is carried out through heating the red mode with sodium carbonate in a graphite crucible at a temperature range of 1000 degrees centigrade for 1 hour. So first you carry out the heat treatment of red mode with sodium carbonate, and then you that is you leach the that is you make a you heat treated material with the water for extracting or removing some soluble material from the red mode. So during heat treatment with the sodium carbonate, it is found that some metallization was exactly happened. Red mode contains iron oxide, aluminum oxide, some part of the titanium oxide. But when you are heat treating, so after heat treating, it was found that some part is metallized, and that is a good thing. That, as I have already told you, in the slag material also, in the electrolysis process we usually prepare a conducting material. If you take a source material conducting, then it is a better electrolysis will happen. So that thing is it is one of the most important concept behind the why I am treating the red mode before electrolysis. And another part is that if any silicon or aluminum is there, they can be removed as sodium silicate or sodium aluminate by heat treatment with sodium carbonate and after water leaching. So all this material will be removed. Now you can get the material contains iron, titanium, if nickel, chromium, likewise. So then what will happen? The resulting dried residue after water leaching is taken in a stainless steel wire mesh. So after water leaching, the resulting mass is dried properly, and it is taken in the stainless steel wire mesh basket. We have prepared a basket-like structure from the stainless steel wire mesh, and here what I am doing, I am not preparing a compacted mass. As I have already told you, first you prepare the powder into compacted mass. And in the slag case, it is not required to make a compacted mass because it is already in the solid form or compacted form. And but in this case, we are not making the in compacted form. Going to make it a compacted form. So then we have prepared a stainless steel wire mesh and we put directly the powder, and then we compact it with the along with the stainless steel mesh, and it is the whole system is connected to the steel rod and dipped into the electrolyte. So I will show you the figure. This is the figure. You can see it is a basket structure where we have kept the pre-treated red mode, and it is connected to the current collector. The current collector is connected to the negative terminal of the DC source, and it is the graphite crucible which is connected to the positive terminal of the your DC source. So, and then it is the molten electrolyte. So what will happen during electrolysis? The basket containing the red mode, containing the various metal oxides, the metal oxides, the oxygen will be removed to the electrolyte, and after passing through the electrolyte, it goes to the graphite crucible, and again comes out as CO2 or CO. So what is the cell voltage? The cell voltage is 3 volt, and we have kept the time period at 1 hour, and here we have electrolyzed the material at 1000 degree centigrade. Usually you prefer to do it 900 to 950, but here specifically it is for a typical experiment, it is 1000 degrees centigrade. So after electrolysis, you can see here, this is the actual red mode XRD. What is the phase analysis, and after the heat treatment, some metallization of iron metal has happened, but after electrolysis, you can see the material phase what you have analyzed. This is mostly Fe, Fe2Ti, FeTi, FeNi, NiCr likewise. So various phases we observe that shows the presence of titanium, nickel, chromium are there in the material. Again, we have characterized the material by the ACM or EDS, and the area analysis was carried out, and we found that it contains mostly Fe. Iron is the very important of the major material, followed by the nickel, chromium, titanium. They are also present. So different area analysis we have carried out, and in most of the cases we are getting FeNi, and so we thought that it is mostly a FeNi alloy containing some amount of titanium and nickel. So if you see that the whole process consists of that is a series of your procedures. Like the first one is your red mode is heat treated with sodium carbonate, and after heat treatment in the graphite crucible, it is taken out, and the material is like this. this heat treated mass, and this heat treated mass is water leaching with the water to remove any kind of water soluble materials. Then after drying the leached mass, we have taken this material into a stainless steel basket type structure, and we have put it here in the basket type material. Then we have connected it to the current collector of the stainless steel rod, and we have carried out the electrolysis. After electrolysis, the material is recovered from the basket and it is water washed. And after water washing or acetone washing, we are getting this kind of FeNITICR alloy powder, and it is produced in the powder form mostly. And in this electrolysis process, whether you are taking in the compacted form or in the powder form, mostly we are getting in the powder form. Sometimes some sintering may happen due to the high temperature, or if you increase the electrolysis time. But here, particularly for the red mode, we are getting this kind of material from the material like FeNITICR alloy in the powder form. So in this topic, we have discussed two types of alloy preparation from the two different starting materials. One is titanium reslag, another one is red mode. And in particularly in the red mode, an alloy containing iron in significant amount with some amount of nickel and low chromium and titanium has been produced. And as you know, iron is a very good structural material. But when you are adding some titanium or nickel or chromium to this iron, then its properties are greatly enhanced, can be used in anti-corrosive in corrosive environment in high temperature applications. So it can be a very good structural material. And if you are preparing it from a waste like red mode, or if you are byproduct like red mode, then that can provide you one that is a economical aspect of treatment of the red mode. And one most important thing is that if you when we are treating the red mode with the sodium carbonate, it exactly does some metallization, partial metallization, and that will enhance that will facilitate the electrochemical reduction process. So and if you see the electrochemical reduction process, it is comparatively very low temperature operation if you compare it as the smelting process, where it is carried out at a 1500 to 1600 degrees centigrade, where the fabrication of the reactor chamber is difficult to maintain at that such a temperature. And in this process, we are not going for that high temperature. You are using a very cheap and environmental friendly electrolyte that is very highly soluble in water only. So the product is only washed with the water that is sufficient. And on the point of the view of the environment, on the point of view of the economical concept, this process is found to be mostly promising, and it can produce a very valuable structural material of iron alloy containing very important alloying elements like nickel, titanium, chromium from the red mode, which is called usually one waste. So this is a very important aspect of this electrochemical process. So with this, I want to conclude, and thank you all of you. Be patient to listen my talk, and thank you for the organizing committee, specifically Dr. Sunita Rautrai.
Thank you, madam.
Okay. Any question?
Now it is open for discussion.
Yes. So should I share the PPT again for the question session, or it is okay?
No, not required, not required.
Okay.
So participants, any question you can ask.
I think no question.
I think you have explained everything so nicely, so there is no doubt from the participants.
Okay, but I hope some questions should be there from the participant so that it will be a good discussion. Okay, madam.
Okay, so thank you, madam, for such a nice presentation. So this was the last session of AICT approved 5 days faculty development program on waste technology. So thank you participants for your cooperation and patient hearing. I am also thankful to my team members, Ms. Adyansi Patnaik, Mr. Rakesh D and Dr. Kalinga Bora for their sincere involvement for the success of this program. To the head of the Department of Mechanical Engineering Department, Dr. D.K. Biswal sir, and to the management of C.V. Raman Group of Institutions for their cooperation. So now, next the question paper link will be shared in the chat box and also through the mail. And the response of the question paper that will remain open till evening 8 p.m. of today. So participants, any doubt regarding anything? To conclude this program, so any doubt you can ask me. After 5 minutes, I will share the question paper link in the chat through mail, and before 8 p.m. Try to submit that one. And the participant in the AICT platform also, you will be getting one feedback form that you have to fill up there. And that is mandatory. Without that, you are not mindfully, you have to you complete that step. So as there is no question, so here I conclude the session, the 5 days program. So some queries are there in the chat box. Okay, thank you, sir. It is all. It is organized. That is not the not only the credit goes to the organizer. This is the everybody's effort from the participation side also. You have cooperated so much. In the beginning, 1 or 2 days, there is some login issue, but patiently you have. We have tried from our side to. Also, you have cooperated a lot. So thank you all, and hope in future whenever we'll organize this type of session or program, you will be all come to join the program. And this is this time this was in online mode, so we couldn't have much interaction. But when we have any offline program, so that time I hope we will have a good time together. Okay, any specific anything anybody want to share here, you can please. Yes, time limit for the question to submit, that is up to 8 p.m. today. Okay, thank you.
Ma'am, am I audible?